Good. And let me start by saying something about the next lectures. So next Wednesday, Professor Ceola is not teaching because she's busy with the degrees. I can teach, and I booked a room in Via del Risorgimento, so I will send a message. The room is ground floor, room LAMC, but I'm sending a message and I'll explain you where it is for next week. And next Wednesday, we will have lectures in Ravenna because once in a while we have to go there. And it's April 1st. And on that day, you will have lecture by both me and Professor Ceola. So I prefer to go in Ravenna when we are all there. So you make the travel for some more consistent purpose. So next Wednesday, March 25th, we meet in Via del Risorgimento. We send a message. And then April 1st, we meet in Ravenna and in the usual room. Very good. Now, let's start, and as usual, let's make a brief recap of where we are. And we went into extreme value theory, and for the purpose of designing project variables related to climate, environment, etc. And we studied the extreme value distributions, and in particular, let me go down, we focused on two methods, block maxima, annual maxima. We still have to talk, I think, for block maxima and peak over threshold. We still have to talk a little bit about peak over threshold, but let me make a brief recap on, I go down on the GAV distribution, which is here. And the GAV distribution is a distribution that is including as special cases the three extreme value distributions that we have discussed, the Gumbel distribution, and then the second distribution again for upper extremes is the Frechet distribution, and then for low extremes the Weibull distribution. Remember one thing, number of parameters. Gumbel distribution has two parameters. The Frechet distribution has three parameters because it may look, when you look at here, it may look that the parameter is just one, but actually Z depends on, because you may, if you look at these representations here, it looks like the Gumbel has no parameters. The Frechet has one, and the Weibull as one. Actually, remember that in this representation here, the probability is given for the variable Z, which is the rescaled variable. And therefore, rescaling implies two parameters, actually, because the formula for rescaling is what you can see here. Okay, and you see that there is indeed a B and A, two parameters. So the result is that the Gumbel has two parameters. The Frechet has three, because it's alpha plus A and B that are depicted here, and the Weibull three in the same way. So when we jump to the representation that we gave for the GV, you see that the parameters are three, but here the variable is X, and therefore actually it is actually three parameters, and the distribution again is referred to the original variable X. And then what you see here is are the conditions that lead to the Gumbel, Frechet, and Weibull. So first of all, there is a condition for defining the support. The support is the range of the parameters that the distribution covers. Remember that now we have three parameters, and the three parameters are location, which is connected mainly to the mean value. mainly because it's not only the mean value. And then there is the scale parameter that is connected to the standard deviation. And then there is the shape parameters that is defining the behavior of the extremes, and therefore the behavior of the tail, and therefore determines if the tail is light-tailed or fat-tailed. Now, Frechet is obtained, as we said, and I make a brief recap, for xi greater than 0. And then you see the support, x greater than mu minus sigma divided by xi. So it's lower bounded, unbounded above, and this makes it suitable for describing the upper extremes. The tail is heavy. And then there is the vibule, and the vibule is obtained for xi lower than 0. And then we get here the domain, the support, x lower than mu minus sigma divided by xi. So it's upper bounded. And then there is the gamble, which is obtained for sigma equal to 0. For xi equal to 0. And the support is minus infinity plus infinity. Now, remember that when you make the estimation of the parameters for the GV, and then we discuss again the estimation soon, the result that we get determines the type of distribution, meaning that if you get xi equal to 0 or close to 0, then it's a gamble. If you get xi greater than 0, it's a Frechet. Xi lower than 0 is a vibule. And in general, therefore, it's the estimation that determines the distribution. It's not the other way around. So in principle, it is not possible to say, okay, I want to estimate a Frechet over a certain sample. Because if it turns out that the parameter xi is 0, it's not a Frechet. Or if it happens like it happened to me, I want to force a Frechet, and then I get a shape parameter xi that is lower than 0, it's not a Frechet, it's a vibule. And it means that it's upper bounded, which I mean may make it suitable anyway for modeling upper extremes, depending on the goodness of the fit, but there is no way to force a Frechet distribution unless you put a constraint in the estimation, like I want xi greater than 0. I tried to do that because I had a case where indeed I wanted to estimate a Frechet, and I got xi lower than 0. And then I said, okay, let's constrain xi upper than 0, but what I got is xi equal to 0. So the forcing led me to estimate a gamble, but I couldn't really impose a Frechet. Or we could impose it if we say, okay, xi must be greater than 1, but it's not very reasonable. So this is the summary table, and that's it. Now, we also discussed, I think we already discussed the generalized Pareto distribution. Perfect. So the generalized Pareto, again, 3 parameters: shape, location, and scale. Okay, here scale is called beta, and here the third parameter is embedded, is the threshold. Is the threshold because remember that we model with this distribution written here, we model the exceedance above the threshold. Okay, it is very easy to make a substitution. If we want to model the original variable x, it's very easy. You take this last relationship here, you plug for y x minus u, and then you get the third parameter, which is the threshold. But usually we fix it. We don't estimate it. We fix it. We want to fix it because we want to have a control on the events that we select basing on the threshold value. And then if we fix the threshold, then it turns out that the generalized Pareto has actually 2 parameters. not 3, because the third one, it is fixed by us. It's like we said, okay, let's estimate a GAV and fix the location parameter. So when you fix one parameter, of course, the number of estimated parameters, this is the correct way of saying it, the number of the estimated parameters of the Pareto is 2. Perfect. And then you see that if Xi is greater than 0, we have a heavy tail, Pareto-like. If Xi is equal to 0, then we have an exponential tail. And it's a Gamble type, but it's not really a Gamble because we fix the location. And if Xi is lower than 0, we have bounded tail physical limits. And then you see here that indeed the substitutions here is done. And here you see 3 parameters, but on the other hand, again, U is the level of the threshold, which is fixed. Okay, and then we talked about the return period. Now, let me just here, I included additional details on the return period because I want to make clear what is the meaning. And second, I want to make clearer what I said, what is the unit of the return period when we estimate it. What is the unit? So, and last time I very briefly said, if you use annual maxima and you estimate the return period like it is written here as the inverse of the probability of exceedance, then T comes out in years. But I want to give more details on that. And indeed, here I changed this line where T is expressed in terms of delta T, where delta T is the average time step between observations. So let's discuss a little bit this, because when you use peak over threshold, the time step between the events that you have selected is not the same. It's not like annual maxima. It's 1 year, 1 year, 1 year. In this case, it's different. So let's focus then on this box, which I included a couple of days ago, return period. So first of all, we already mentioned the definition, and please remember it because this is a recurrent question. The return period, which it's also known as a recurrency interval or a return interval. Anyway, the most used terminology is return period in the literature, is the average time between events, and in general, like earthquakes, floods, landslides, or river flow, exceeding a given magnitude to occur. So it's the average time between events exceeding a given magnitude to occur. Okay, and the reciprocal value of the return period is the frequency of exceedance. But of course, we are not talking here about the units of the return period. So the theoretical return period between occurrences, as we already mentioned, is the inverse of the average frequency of occurrence. Okay, and so 2 sentences saying the same thing with different words. Okay, words. For example, let me give an example. If you have a 10-year flood return period, it has a 10% chance of being exceeded in any 1 year. And the 50-year flood has a 2% chance to be exceeded in any 1 year. Now, in mathematical terms, because it helps us to understand, as mentioned above, then the probability is the inverse of the return period, and the return period is the inverse of the probability. Okay, and as I said above, T in terms of units is expressed in terms of number of delta T. So let us suppose that the observation period, let's give an example, is 10 years long. Okay, so if the probability is estimated with the annual maxima, then delta T, the average time step between observations, is 1 year, of course, because you get 1 observation every year. So the return period is expressed in years. Then, if, let's say, the probability of exceedance is 0.1, the return period is given by inverse of the probability, 10 years. This is clear. Okay, now let's look at the peak over threshold. And let's say that 7 events for the same period of 10 years are selected. So less than with the annual maximum, 7 events. Now, the average delta t between events is 10 years divided by 7, because if I selected 7 events, the average time between them is 1.43 years. And therefore, if the probability is still 10%, 0.1, the return period is given by 1 divided the probability, which is 10, times 1.43. So it is 14 years, 0.3. And this is something that you can understand because if you select less events, the frequency of occurrence of these events, of course, in 10 years is lower. And therefore, when you compute the inverse of the frequency, yeah, perfect. Yeah, please. Okay, let's wait for another student joining. Yeah. Hello. Hello. Very good. You can make yourself comfortable. It's good if you sit there because you see the screen.
Yeah.
On the other hand, if you want to use the other chairs for putting your jacket, feel free. You wrote to me an email. Okay, that's fine. I am getting information for the internship is not easy, but anyway, I will. I will check for that. Okay. Yeah, no problem. So I didn't reply to your last email, but I have it in mind. Okay, very good. So we were discussing about the return period and in particular about the units, starting from what you already know, that the return period is defined as the average time between events exceeding a given magnitude. And the return period is given by the inverse of the frequency of exceedance in the inverse of probability of exceedance. And an important thing, and this is what we were discussed, is the unit of the return period. Because of course, if you say the return period is the inverse of a probability, you are not specifying the units. And therefore, the inverse of the probability is a number, dimensionless, because the probability is dimensionless. And therefore, we have to discuss what is the unit of the return period t that we estimate as the inverse of the probability. And so let's refer to a practical example. Let's suppose that we use the annual maxima method. And then what is the time step between observations? The time step between observations is 1 year, because it's the annual maxima is 1 observation per year. So between each observation, each pair of observations, we have 1 year. So if the return period is computed for a probability for exceedance of 0.1, say, then the inverse of the frequency of exceedance is 10. 10 what? 10 times the time step between observations, and therefore it's 10 years. Because a frequency of 0.1 means that once every 10 observations, I get, on average, that precise given value of the observation. So it happens once every 10. And therefore, given that I get 10 years to get 10 observations, the return period is 10 years. And what is basically the conclusion? That the unit of the return period is the time step between observations. This is the unit. The time step between observations is 1 year. And therefore, if I get a value for the return period of 10, the unit is years. But what about the peak over threshold? In the peak over threshold, I make a selection of events, and the time step between them is varying. So let's suppose that with this over the same 10 years period, I select 7 events. The time step between them is varying. I can compute the average. The average is 10 divided by 7, 10 years divided by 7 events, it means 1.43 years. Good. Now, then the inverse of the probability of exceedance of 0.1 is again 10, but the unit now is the average time step that I just computed. So it is 10 times 1.43. So it is 14 years for the same probability of exceedance. So for the annual maxima, probability of exceedance of 0.1, return period 10 years. For the peak over threshold, with 7 events selected, probability of exceedance 0.1 means a return period of 14 years. This is quite easy to be understood if you think that if you select only 7 events instead of 10, it's clear that you get values of the magnitude of this event that is larger, okay? Because if I select 10, of course, the average of this 10 is lower than the average of the highest 7. And therefore, you get, for instance, a location parameter that is larger for the estimated distribution, which is a different probability distribution. This means that for the same frequency of exceedance, for the same probability, the distribution gives back an estimated value that is larger because the distribution was estimated over larger events. And therefore, it's clear that also the return period, expressed in years, must be larger. And this is why in the second case, I get 14 years of return period instead of 10, because the distribution delivers back an estimate that is larger. And it's larger because this distribution was estimated over events that are larger. Now, this is quite obvious, but I saw also very distinguished professors ignoring this and expressing the return period in years with the peak over threshold, even if it's not the case. Or you can express it in years after the scaling, because the unit is, in general, the average time step between observations. And just this consideration help you to reach one of our targets, that when you apply a method, you understand, you have a full comprehension of what is behind it. Okay, so no matter what method you use, do you use a probability distribution? Okay, that's fine, but you have to get a full perception, not just blindly trust what the computer gives back to you, which is something that is occurring more and more today, because we have softwares, as you have realized, that do everything. And therefore, it's very easy to upload a software, as we will see, because now we make an exercise. It's very easy to upload a software, just press enter, and then we get a result. But it's very important that you get an understanding of what is behind it, because for many reasons, we are not discussing again. One of the reasons is that you are taking the responsibility for what you do, and therefore you may need to defend it. A second reason is that computer programs sometimes make mistakes, and therefore, if you want to make be able to correct these mistakes, to at least to catch that, you have to know what is behind, and above all, your understanding of what you are doing makes your contribution more distinguished. Whatever you do, if you make research, if you make practical works, I mean, sometimes we say in Italian, sa quello che fa, he knows what he does, they know what they does, and it's gender neutral. And this means that, okay, a person that knows what this person is doing means that it's a person deserving trust, okay? Also for politicians, we say they know what they do, and this is a way of providing support, okay? Okay, good. Now, let me just remind you the estimation problem. And we discussed the method of moments, the maximum likelihood, and I mentioned that there are other methods. And we don't discuss the other methods. The most traditional one are the method of moments and the maximum likelihood. We discussed why they are traditional. The other methods, which are more recent, have been introduced, in particular the probability weighted moments and L moments, to cope with the reduced number of observations. Remember that the estimation problem is always easy, whatever method you use when you have a lot of data. The estimation problem becomes a challenge when you have a limited amount of data or no data at all. And we didn't discuss this, what to do with no data at all, but we discussed what to do when the sample size of the observations is small, and this happens frequently in environmental sciences. And we said that indeed these methods that L moments, probability-weighted moments are more robust. We said more reliable. You can say more reliable. Robust is a technical term in statistics, which means not very precise. I am simplifying it, but affordable, trustable, okay, deserving trust. And indeed, if we want to be able to get estimates that are more solid, we may prefer these probability-weighted moments, L moments, and there are other variants of them. But I want to emphasize once again that the method of moments, I think it's clear. I want to emphasize the two classical methods, how they work, because even in this case, it's important that you get an understanding of it. Method of moments, I think it's clear. It means equating some statistical behaviors of the distribution with statistical behaviors of data. So mean is equal to mean, so average is equal to average of the observations is equivalent to the average of the distribution and the standard deviation and the skewness, which is the third order moment. And then we equate them, and this is okay. Maximum likelihood, I want to stress once again what is maximum likelihood. It is given by a function for which we research the maximum, which is called this function, likelihood function. And you can find a lot of links over the web. And let me go to the likelihood here. Likelihood function. The likelihood function depends on the distribution, of course, because it must be a function of the parameters. And the target is to maximize, or let's say, optimize this function by seeking the parameter values that optimize it. And therefore, the parameter values that optimize the likelihood then are our estimates. And why I said optimize instead of maximize? Because sometimes we seek the optimum, the maximum, by minimizing another version, a manipulated version of the likelihood function. And so sometimes, for instance, we take the negative likelihood, or we transform the likelihood so that it takes only negative values, and we have to find the most negative. And we make this transformation of the likelihood function, these transformations, because looking for the optimum may be easier after data transformation, okay? So this likelihood function is something to be optimized. And what is the likelihood function? What gives the likelihood function? The likelihood function, as I said last time, and it gives the probability of getting from the distribution the observed sample of data. So you maximize this probability. So given that these data were observed, they are true, what are the parameter values that make the selected distribution able to give the max probability for these data? Given that they occurred, it should reach in principle probability 1, observing them, okay? And then we compute a unique function that gives a synthesis of the probability of all the data. And therefore, you understand that if the probability distribution is complicated, also the likelihood function is complicated. And then sometimes we need to compute it by us making simplifying assumptions. Okay, this is the likelihood function. And then I gave an example of a simplifying assumption when I said, okay, let's take this homemade distribution of model parameters, okay? Where is it? Homemade distribution. We simply minimized the absolute difference or the square difference between the probability given by the distribution and the frequency of not exceedance. This is a simple likelihood, but it's not a real likelihood. It's a simplification, okay? And here I explained everything for that. So just keep into account likelihood. It has some advantages with respect to the method of moments. It's computationally more intensive, so this is a disadvantage. And another disadvantage is that sometimes we need to rely on simplifying assumptions. But we already experienced that the likelihood, maximum likelihood estimation is more reliable, because in the example that we provided last week, we realized that the goodness of fit test was more reliable by estimating the Gamble parameter distribution, the Gamble distribution parameters with the maximum likelihood rather than the method of moments. So, of course, when it's possible, let's always take the maximum likelihood. And in fact, if you take the softwares that are already pre-prepared into R, into Python, usually they estimate the distribution parameters with a proper likelihood. And remember that you have always to be careful when you get the output, because you should make sure of what are the assumptions of the likelihood. For instance, there are some likelihood functions which are called the Gaussian likelihood, which assumes that the distribution is Gaussian, and this is never the case for us, because we have always, when we talk about extremes, we always have distributions that are long-tailed, are not symmetric, but still the likelihood is computed by assuming a Gaussian likelihood. And so make sure that you know these assumptions, and make sure that when you search for the max, and this is what we did last week, we used Optim to search for the max. These are numerical routines that look for the optimum of a function. And make sure that they reach convergence, because these numerical routines, what they do is to make a search, a random search, that is not really random because it is somehow guided. But sometimes they get disoriented, they fail, and then they give to you a result that is the best that they obtained, but they also tell you in the warnings, warning, I didn't converge, so I'm not really sure that this is the optimum. It is a maximum that I found, but I'm not really sure that is the absolute maximum. And therefore, make sure that when you use these routines, in a way, you are confident of what you get. And if you are in doubt, why don't estimate with a very simple computation with the method of moments the parameter values? You test them and you compare if they look similar, and if the maximum likelihood estimation gives to you a better fit than the method of moments, you are reasonably safe and your responsibility is waived. On the other hand, if you find that the maximum likelihood estimation is worse than the method of moments, you should reject it. Okay, reject it and say, okay, let's take the method of moments estimates, or let me try another time with another routine. Because you have several of these routines. The one that is embedded in R, Optim, is very nice because it's very easy to use, but also in R you have several other ones which are maybe more demanding in terms of computational time, but on the other hand are more reliable. What I want to propose you today, and there is one thing that I wanted to tell you, and I go back because in principle this lecture, as I said, is finished, but let me go back to the example that we made in, I think it's here, real world data example. We did this example before starting talking about distributions because I wanted to start with a numerical example, and this is in Python, is not in R. And this example refers to data that we took from New York City, rainfall data, and for a limited time. And here, what we did is, in order to estimate the distribution, let's try to go back a little bit. This first part is just download of the data from the web. And as I said, you may try different locations. I'm not sure what is the coverage of this database. And this is daily data. And It is an interesting database. It covers up to now, basically. And then we applied the block maxima. And the block maxima, what we did is to import the libraries. Okay, so matplotlib is basically a library to make plots, high-level plots. And then we imported this library, PI Extremes. PI Extremes has a documentation that you can study. PI Extremes is a Python library for estimating extreme value distributions. And in fact, we imported NumPy. NumPy is a basic library of Python. Remember that Python has no libraries embedded and only basic, very basic functions. And anything that you want to do needs to be uploaded in libraries. The same for R, but R has a number of default routines larger than Python. Okay, and remember another thing: Python doesn't save, so it's not like R that when you get out from it, it offers the option to save it. And if you save in R, when you go back, then you upload automatically the previous database. In Python, when you go out from the program, everything is lost. And therefore, you have to make sure that everything that you do is repeatable. And if it's not repeatable for any reason, or it's repeatable with a long computational time, you have to save the data manually, which means exporting the numbers to text file, exporting the graph to PDF, whatever, okay? And then this model, this library PI Extremes. So first of all, here in these instructions, there is the instruction of getting the extremes. And here you see method BM means block maxima. So you tell the library, take the block maxima. These are daily data. And they take block size 365 times 24 because it's the leap years, you know, the number of days on average is this is a very precise value, because you know that every 100 years we need, or 200 years, I don't remember, we need to recover one more day, or no, every 100 years there is no 29 February in the 00 year. So 29 February 1900 was not there. 29 February 2000 was there because in the computation every like 1000 years we have to anyway keep. So for 200 years keep the 29th of February. So this is the exact duration of the year. And then I don't know how they do in extracting the extremes here, given that it's impossible to extract the extreme for fractional numbers. So I'm not sure what they do. I think that you get the same extractions for a short duration like here, 25 years, you get the same numbers if you put block size 365. Anyway, it doesn't matter. And then there is the definition of the model. So basically, fit model means I'm defining a variable, and then I am defining the value of the confidence, significance level. Oh, this is the confidence level. But they are related. We talked about the significance level of a test. The confidence level is 1 minus the significance level. So we talked about a significance level of 0.05, and this 0.945 is the confidence level. And then here there is the fit of the model. Okay, the fit of the model. This plot just shows the annual maxima that I extracted, and here there is the fit of the model. And you see model MLE. Distribution none, what does it mean? That it estimates the GV, because block maxima GV, and if you put none in the distribution, it doesn't force any distribution and gives to you back the parameters of the GV, and you decide, and you see what the distribution is, depending on the value of the shape parameter, basically. If you want, you can force a distribution here, and these other arguments, let's forget about them, because we should look at PI extremes in order to at the guidelines, instructions of the program. But basically, what we did without realizing it, and now we can realize what we did. What we did is to estimate with the maximum likelihood and without imposing any distribution. I think that it allows for specifying rather than MLE, MOM, which means moments. But if you're interested, you have to check. If you look for PI streams in the web, you find a document of about 30 pages. And then here there is the fit model. So fit model contains the results. And then you see that here, summary, it gets a summary, and for return periods corresponding to these values, which means give me back the extreme estimated for these return periods, alpha 0.95 is the confidence level, and then a number of samples, 1,000, because I think that it generates 1,000 samples of simulations from the distribution. I don't remember for what purpose. And then there is, you can apply the POT, peak over threshold approach, and therefore get extremes with the value of the threshold that is fixed. And then there is model, the fit is model pot fit model. And then model pot is specifying indeed that the model is peak over threshold, and it works. We didn't try with the peak over threshold, so you may want to try and let me know if it doesn't work for some reasons. Just wanted to go back and explain that now, based on your knowledge, you can better understand with a better comprehension what we did at that time. Okay, very good. Now, let's go to the new thing today, and experiential learning, peak flow estimation for the Po River at Ponte Lagoscuro. Okay, so this is an exercise. If you have the opportunity, my suggestion is let's try to work at it together, because the best way of learning is to do things. And if you can't work on it now, because, for instance, or you don't want, because, for instance, maybe that you want to concentrate on what I'm saying, that's fine. My suggestion is try to repeat this, because I think that it gives to you the opportunity in R, but you can also easily translate in Python. It gives to you the opportunity to better learn. And